Hi folks, we're going to take a look at question 4D from the Unit 3 assignment. So they give us this function here and they want us to determine the critical points and whether the critical point represents a local max or a local min. I guess neither. And they also ask whether the tangent is parallel to the x-axis. I think what they're asking there is this a critical point where the derivative exists or where the derivative doesn't exist. So if it does exist, then the slope of the tangent will be 0 and hence will be parallel to the x-axis. Or if it's something like a cusp or a corner where you won't have a tangent at that point. Okay, so we're going to have to find the derivative here, but because this is a logarithmic function, we should probably determine what the domain is to make sure that whatever values we get are actually valid. In other words, that they're in the domain. So in order to be in the domain of this function, you need the input to be strictly greater than 0. So you need x cubed minus 3x squared minus 9x to be greater than 0. Okay, so let's try to factor this here. So we can easily factor out an x, and we're left with x squared minus 3x minus 9. Okay, unfortunately when we try to factor this thing here, it doesn't look like it factors nicely. So we will have to use the quadratic formula here to find the zeros. So x is equal to negative b, so 3 plus or minus square root of b squared, so 9 minus 4 times 1 times negative 9 all over 2. So it's 3 plus or minus, and so here we've got 9 plus 36, so that's 45, square root of 45 over 2. Okay, and that's approximately equal to, let's do this here, so 3 plus square root of 45 divided by 2. So we've got 4.85 or 3 minus square root of 45 divided by 2. Okay, negative 1.85. Okay, so we need this cubic expression to be greater than 0. So I'm going to use my old trick of knowing the end behavior of this function. So my 3 zeros here are negative 1.85, whoops, 1.85, we've got 0, and we've got 4.85, and given that the leading coefficient is positive, I know that my function, the input to the function will only be positive in this interval between negative 1.85 and 0 and greater than 4.85. Okay, so anything that shows up in these two intervals we won't accept. Okay, so now that we know the domain of the function, let's go ahead and find the derivative. Okay, so derivative of a logarithmic function, so we'll make this our u. Derivative of ln u is just 1 over u. So 1 over x cubed minus 3x squared minus 9x times the derivative of the numerator, which is 3x squared, not derivative of the numerator, but derivative of the input, our u, 3x squared minus 6x minus 9. Okay, so let's see if we can factor this in the numerator. So let's take out a 3. We're left with x squared minus 2x minus 3 all over that denominator. And luckily this does factor nicely, so 3, and that's x minus 3, x plus 1, so x cubed minus 3x squared minus 9x. Okay. Excuse me. Okay, so anything that makes the derivative not exist is what's going to make the denominator 0, and we know that anything that makes this expression 0 won't be in the domain of the function. Okay, so those won't be critical points. So our only possibilities are what make the derivative equal to 0. Okay, which is the numerator here. So x can be equal to 3, or x can be equal to negative 1. Okay, and we take a look. Negative 1 is in the domain of the function. Okay, but 3 is not. okay, because it makes this input negative and hence can't be in the domain of the function, can't take the logarithm of a negative number. So there we go. We're left with only one critical point. Okay, so first thing we have to do is determine whether this is a maximum or a minimum. Now, since the derivative is equal to 0 at this point, we already know that the tangent will be horizontal, so parallel to the x-axis. So we've answered that second part, but let's see if it's a max, min, or neither. Okay, so let's determine the increasing or decreasing behavior before and after -1. Okay, now this is where we do have to be careful because we have to pick x values that are actually in the domain. So here I can't pick -2, which would be the normal number I would pick before -1, because -2 isn't in the domain of the function. So I'll pick -1.5, okay? And above -1, sort of same thing. I can't pick 0. That makes the input 0, and so not part of the function. So I'm going to pick -0.5. Okay, so you see here, this is why it's good to determine the domain. The domain of this function before I start applying any of this here. Okay, so let's put in -1.5. Okay, so here we've got this will remain negative. Okay, and then -1.5 plus 1 is still negative, so you've got two negatives in the numerator, so the numerator is going to be positive, and the denominator, well, I already have my little sign here. I know that the denominator is going to have to be positive when x is equal to -1.5. So positive over positive, we have increasing on the left. So let's see if we have decreasing on the right or if it keeps increasing. So let's put in -0.5. So again, this is going to be negative, but this second one's going to be positive. So negative times positive is negative. And in the denominator, well, you know, these things have to be positive in order for them to exist. Okay, remember, input to the natural logarithm. And let's confirm on our graph that, yeah, -0.5, positive there. So that means it's decreasing to the right of -1. So since we're going from increasing to decreasing, we have a local max at, okay, and they're asking for the critical point, so we need -1, and let's stick this back into our original function to get the y value. So we have this -1 cubed is still -1, minus 3 times -1 squared, that's +1, so -1 minus 3 is -4, and then minus 9 times -1, so that's going to be +9, so -4 plus 5, -4 plus 9 is equal to 5. So this is going to be ln 5. Okay, so there's our point, and we have that the tangent is parallel to the x-axis, okay, since the derivative is 0 there. Okay, so again, just to recap, we're looking for critical points, so we find the derivative to determine where it's equal to 0 doesn't exist, and we determine that the only critical point was x equals -1, and just be careful about only working with input values that are actually part of the domain of